Hi everyone, my name is Irene Koh. Today I will be presenting my IoT assignment titled Smart Irrigation System using IoT. For this project, I selected Taman Pertanian Johor as my case study. I visited the site, identified the existing farming problems, and proposed the IoT Smart Irrigation System to improve irrigation efficiency. Now, let us start with the site overview. As you can see, this is Taman Pertanian Johor, located at Jalan Kongkong, Masai, Johor. This is a government-operated agricultural park covering more than 100 acres. Besides farming activities, it is also used for agricultural research, technology demonstration, and farmer training. There are many types of crops grown here, such as vegetables, bananas, coconuts, papaya, and lemongrass. Because the farm is very large, I think it is a suitable place to implement an IoT smart irrigation system. So, during my site visit, I've observed different cultivation areas. As you can see from the photos, there are vegetable farm, plastic mulch farming, banana plantation, coconut plantation, papaya plantation, and lemongrass plantation. Different crops need different watering schedule. This makes irrigation management more challenging, especially over a large farming area. Next, I would like to explain the current farming practices and challenges I've observed during my site visit. Firstly, irrigation is still carried out manually. Farmers need to switch on the water pump and control the irrigation process themselves. This requires time and continuous supervision. Second, farmers manually inspect both the crop and the soil condition before deciding whether irrigation is needed. This method depends on personal experience and may not always be accurate. Third, the farmer also need to check the water tanks manually to ensure there is enough water for irrigation. They have to physically visit the tank, which is time consuming, especially for a large farm. Now, the first challenges is the large farm area. Since Taman Pertanian Johor covers more than 100 acres, it is difficult to monitor every cultivation area efficiently. The second challenge is that farming activities require a lot of manpower. Workers need to inspect different field and irrigation equipment every day. Another challenge is the lack of real-time monitoring. Farmers only know the field condition after they visit the site, so the problem cannot be detected immediately. Besides, water wastage is also a common issue because irrigation is based on manual judgment instead of actual soil moisture condition. This may lead to overwatering or unnecessary irrigation. And also, the problems such as dry soil, low water level, or equipment failure may only be discovered during routine inspections, causing delays in taking corrective action. Therefore, to overcome all these challenges, I propose an IoT-based smart irrigation system, which I will explain in the next slide. Next, I will explain my proposal of IoT solution. As you can see, my system consists of three layers, which are perception layer, network layer, and application layer. The first is perception layer. This layer responsible for collecting data from the farm. I propose three sensors. The soil moisture sensor to measure soil moisture, the DHT22 sensor to monitor temperature and humidity, and the water level sensor to detect the water level in the storage tank. The sensor readings are processed by the ESP32 microcontroller. Based on the collected data, the ESP32 automatically control the solenoid valve and water pump whenever irrigation is needed. Well, the next is the network layer. The ESP32 sends the collected data, sensor data through LoRaWAN to the edge gateway. The edge gateway then forwards the data to the cloud through the internet. The last layer will be the application layer. In this layer, the data is stored in the cloud database. Farmer can monitor the farm using the mobile application and dashboard. The collected data also can analyze, and SMS alerts are sent automatically whenever abnormal conditions are detected. So the overall data flow is very simple. First, the sensor collects environment data. Next, the ESP32 processes the sensor reading. Then the LoRaWAN transmits the data to the edge gateway. After that, the data is stored and analyzed in a cloud database. Finally, the farmer can monitor the farm through the dashboard and monitor and mobile application, while SMS alert notify them immediately if any abnormal condition is detected. Now I'll explain the proposed IoT architecture, and I'll move on to the communication protocol that I selected for this project. So the protocol that I choose is LoRaWAN. As you can see from the comparison data, I compare to Wi-Fi, Bluetooth, Zigbee, and LoRaWAN. For this project, LoRaWAN is the most suitable choice because it provides long communication range, very low power consumption, reliable outdoor communication. And since the farm covers more than 100 acres, LoRaWAN can transmit data efficiently across the whole site. Next, I will explain the proposed network topology and how edge computing works in this project. As you can see, I selected a star topology. So all the ESP32 sensor nodes communicate directly with one edge gateway. The edge gateway processes the collected data before sending it to the cloud. And this will reduce the bandwidth usage, improve response time, and save cloud storage. Next, I will explain the expected benefit and key performance indicator, or KPI. So for this proposed IoT smart irrigation system, as you can see, the objective of this system is not only to automate irrigation, but also improve efficiency and reduce manual work. So the first KPI is water consumption. Currently, irrigation is done manually, so farmers may use more water than necessary. By using soil moisture sensor and automatic irrigation, water is supplied only when the soil is needed. Therefore, the target is to achieve approximately 20% reduction in the water usage. So the second KPI is manual inspection time. At present, the farmer need to inspect crops, soil condition, and water tank every day. With the proposed IoT system, these conditions are monitored automatically in real time through sensor. As a result, the target is to reduce manual inspection time by about 40%. So overall, this KPI demonstrates that the proposed IoT solution can improve water efficiency, reduce labor, and increase farm productivity. This measurable improvement also show that the system provides clear benefits and support the goal of Industry 4.0 in agriculture. And now I will conclude the overall project and summarize how all the proposed components work together. So in conclusion, my proposed IoT smart irrigation system combine environmental sensor, ESP32, LoRaWAN, edge gateway, and cloud technology. This system helps to solve current farming problems by reducing manual work, improving water management, and providing real-time monitoring. Overall, I believe this solution is practical and cost-effective and suitable for Taman Pertanian Johor. So this concludes my presentation. I hope my proposed IoT smart irrigation system can improve farming efficiency and support sustainable agriculture at Taman Pertanian Johor. I hope you enjoy my presentation. Thank you very much for your attention.